So thanks to the organizers. I'm going to be talking about some things which maybe I was thinking about many years ago, but started thinking about again more recently. So Baues-Wirsching cohomology and its connections with other cohomology-like things. So I say joint work in progress with Imma, Frank, and Simona, but that's talking about the recent stuff. The older stuff was joint work with Baues and with Mamuka Giblazzi and people. Okay, so let me just start with some of the very early. Oh, why can't I change page? Okay, very early definitions. So starting with the setting up what the coefficients for Baues-Wirsching cohomology are. Going to start off with what Baues would have called the subdivision category. Other people call the twisted arrow category. No, maybe Baues would call it the factorization category. So the factorization category of a small category, the objects of the factorization category are the arrows in the category, and the hom sets are the factorizations. So here's a little picture of an arrow between F and F dashed. It just means that there's a way of getting F dashed from F by precomposing with some alpha and postcomposing with some beta. Okay, so you have identity arrows and composite factorizations in the obvious way. A factorization of a factorization is a factorization. And then Baues and Wirsching defined their cohomology starting with their natural systems of coefficients. So the coefficients were systems of abelian groups given by functors from this factorization category to the category of abelian groups. So an abelian group for each arrow in C, that's the object. And instead of saying for each factorization we have an arrow, we could say that for each precomposition by alpha, we have an abelian group morphism from DF to DFA. And for each postcomposition beta, we have a map from DF to D beta F. Okay, so there are abelian groups for each arrow in your category, and there are natural postcomposition and precomposition arrows between these abelian groups. Okay. Then from this, Baues and Wirsching built up this enormous cochain complex. So it's fairly simplicial. It's relevant of lots of simplicial things. It's also reminiscent of Hochschild because it's going to have like little actions left and right or pre and post actions. So we can talk about a bit more about that later. But for the moment, just consider all of the simplices in your nervial category. So all chains of any length of morphisms in your category. Okay, so any chain will have its long edge, just the composite of all the simplices, the map from C0, from Cn to C0, and use this as your indexing set for your cochain complex. So your cochain complex in degree n will be the product over all of the simplices of the abelian group associated with the long edge with the composite map. So each map has an abelian group associated with it. You get the product of all of these. Okay, and that's the same as saying, well, for any element in the nerve, you have an associated element. I mean, something in the abelian group, and then you have to say what the co-boundary is on this cochain complex. So if you've got a cochain A, to specify the co-boundary of A, you need to apply it to an n+1 simplex. So you apply it to the n+1 simplex, and the result has to be, well, you can use this precomposition map F1 lower star to the result of the cochain on F2 up to Fn+1, and then you can apply the cochain to compose in the ith place for each I and take the alternating sum, and finally you can do the post-composition, the Fn+1 star, when you delete the last one. Okay, so it's deleting the zero, deleting C0 and applying the precomposition, deleting Cn and applying the post-composition, or just compose some intermediate arrows. So it looks very reminiscent of Hochschild cohomology, for example. Okay. So the cohomology, the Baues-Wirsching cohomology of your small category C with coefficients in this natural system D is just the cohomology of this complex. Okay. There should be no problem so far, but this is a very old definition. There are lots of, in their papers, there are lots of interpretations, both in the sense of, well, you could say, you could just look at the quotes classical cohomology of the category of factorizations. So FC itself is a category, it has coefficients D. Okay, so you could take the cohomology of this category itself. So in this sense, Baues-Wirsching cohomology doesn't look like anything special. It's just it's the cohomology of the factorization category instead of the cohomology of the category itself. Okay. You can also do homological algebra in the category of natural systems. So in the category of functors from FC to abelian groups, you can resolve the constant natural system. You can resolve Z. Okay, take a resolution and then take the cohomology of the HOM from the resolution into your given natural system D. So you can define the Baues-Wirsching cohomology as some sort of X or derived limit of your functor D on the factorization category. Okay, so there's plenty of other ways you can do it. But when I say interpretations, there's also the other way. You can say, well, H2, the Baues-Wirsching second cohomology group, classifies what they call linear extensions of your category by your natural system. So you can set up what you mean by linear extension. So H2 classifies them. And the same with H3. You can set up some sort of what they call linear track extensions of categories. Okay, so given a category and a natural system on the category, you can say what it means to be a linear track extension of the category. So these things are classified by the third cohomology. Okay, so you get some interpretation of what these cohomology groups are. Okay, and the first cohomology is something like derivations as usual. Okay. Okay, let me jump to something that looks completely different. So I want to try and convince you that Baues-Wirsching cohomology is something like a Hochschild in some sense. So I want to jump to monoid in the sense that when you're doing Hochschild cohomology of an associative algebra, well, you can think of an associative algebra as just some sort of monoid in some monoidal category. So this is some later work. We decided to set up the whole idea of arbitrary cohomology of monoids in arbitrary monoidal categories. Okay, so and use Baues-Wirsching cohomology as a test case, and use the category of opera as another test case. I'll talk about that later. Okay, so for one test case, you look at this slice category. Take any set I. So take a set I. Look at the slice category. Look at the comma category. So all sets over I squared. Okay. And then say, if you're given two things, if you're given some f and some g from x and y to I times I, you can define a product map over I times I, just to be, well, you take the product of f times g, you take the pullback along the diagonal, and then you throw away the middle component. Okay. Now, this is a monoidal structure on this slice category, which I want to convince you is exactly what you mean by a monoid in this monoidal structure is a category. Okay? A category in the category of sets. Okay. So first of all, think of it as matrices. So think of your object over I times I as just an IJ indexed family of sets. Okay. And then this product operation says, well, look at where the index k here and the index k here agree with each other. Okay, take the product and take the union over all k. Okay, and this gives you a matrix product of sets, not of numbers, a matrix product of sets. Okay, and now you think, well, that's really what you do when you're composing morphisms. Okay, so a monoid in this monoidal category is, well, it's like a category C where I is a set of objects. Okay, And an object over I times I is just the hom set. So every category for each pair of elements ij in I squared has a set of elements, okay? And then a composition is a map from hom ij times hom ik, so jk to hom ik, okay? Which is like this matrix product I've defined as monodal structure. So you can say that, well, a category is just an example of a monoid in a monoidal category. So we set up the Baues-Tonks cohomology of monoids in monoidal categories and showed that the Baues-Wirsching cohomology was just an example. If categories are monoids, then the Baues-Tonks cohomology is just the Baues-Wirsching cohomology. Okay. Okay, I mentioned operads, but it's not on the slides. So the reason to set this up was you can also think of operads as monoids in the monoidal category of symmetric sequences. So you could take sequences and take tensor products of sequences in a certain way. So that an operad is just a monoid in this sense, okay? And then we can use our BJT cohomology as a way of defining cohomology of operads. That was our motivation then, okay? But for the moment, we're just looking at Baues-Wirsching. So this is a generalization of Baues-Wirsching, okay? I also want to compare it with what's called the comonad or co-triple cohomology. Okay. So for this, here is a really easy piece of simplicial combinatorics. If you're given any simplicial object K, you take what Graham Siegel called the edgewise subdivision. Okay, so the edgewise subdivision of K in dimension n is K2n plus 1. So it looks like it's throwing away lots of information. Okay, the face map, the ith face map from level n to level n minus 1, well, you have to go from K2n plus 1 to K2n minus 1. You do this by using usual DI and the opposite DI, D2n plus 1 minus I. Okay, and the same thing for the degeneracy maps. So the map from K2n plus 1 to K2n plus 3, representing SI in the subdivision, is you do SI and you also do S2n plus 2 minus I. Okay? So you do DI and its reflection and SI and its reflection. Okay. Okay, so here's another specification of the same thing. Look at delta, look at the category of finite sets, finite ordered sets, and order preserving functions between them. So that when you look at a simplicial object, you're just saying, get a functor from delta up to the category of sets. Okay. Then the subdivision, well, you start with K and you precompose it with this functor T on delta. So on delta, what does T do? Well, you know it has to send n to 2n plus 1. How does it send the ordered set n to the ordered set 2n plus 1? Well, you take your ordered set n, okay, and you start your ordered set with 2n plus 2 elements, okay? You put your usual set here, the first n plus 1, and then afterwards you put the same n plus 1 elements backwards, okay? So that's an ordered set with n plus 1 elements to an ordered set with 2n plus 2 elements. Okay, so precomposing this functor, and this functor, well, you can easily see what happens on the order preserving maps. If you have an order preserving map on this side, you can just copy it here and here to get an order preserving map on this side. So this is definitely a functor from delta to delta, and precomposing with this defines the subdivision of K. And once you've done it like this, you can say, well, the same thing is true for co-simplicial objects. Here I've done simplicial, I've done delta op. But if I forget the op, I can do it for co-simplicial objects, and we can get the edgewise subdivision of a co-simplicial object. Okay. For simplicial objects, basic example, if K is the nerve of a category, then the edgewise subdivision is just the nerve of the factorization category. So the factorization category we saw before is just an example of this edgewise subdivision. Okay. If you do the factorization category, it sends arrows and sequences of 3 arrows to factorize. This is like sub K1 and K3. Okay. Okay. why do we introduce this? I see Mamuka is in the audience. Hi, Mamuka. So we have a little lemma here saying that you can compare the subdivision with the original co-simplicial abelian group, okay, fairly easily. You just get rid of the last n+1 faces, okay, and that induces an isomorphism in cohomology. Now, at the time, I say this was a few years ago, this is 1997. At the time, we were we really wanted to find a nice proof. It was true for all co-simplicial objects. We gave an explicit, lots of calculations proof, inductive proof for the abelian situation for co-simplicial abelian objects. Okay, but it would still be nice to know if in the intervening time anybody knows any stronger results than this. Anyway, so what's this got to do with cohomology? Well, the point of this lemma was that we can use the Baues-Wirsching-Tonks co-chain complex, which is like Hochschild, and compare it with another standard construction. Okay, the co-triple cohomology says, well, if you can look at this category of left-right bimodules over some monodal category V, okay, and then you can forget the bimodule structure. So if you've got a bimodule over an object X, you can forget the bimodule structure and get an object in the slice category V over X. Or you could take the free bimodule on an object over X, okay, and get an object in this category. Okay, if you iterate free, forget, well, the free bimodule is going to add two copies of X, one on each side. Okay, so if you do this n times, you will have like 2n. If you start with one copy, you get 2n plus 1 copies of X. Okay, so this subdivision lemma is just saying in the Hochschild cohomology type thing, you have n copies of X, and in the co-triple cohomology, you have 2n plus 1 copies. And if you take the cohomology, even though the complexes are completely different, okay, the complexes, one is much bigger than the other, okay, but we take the cohomology, you get the same thing. Okay, so the BJT cohomology of a monodal category coincides with this co-triple cohomology of doing free forget on the bimodules. Okay, just like with abelian, so just like with associative algebras, you think of it as a bimodule over itself. Okay, so this tells you, well, if the Baues-Tonks cohomology is a generalization of Baues-Wirsching cohomology of categories, that tells you Baues-Wirsching cohomology of categories also agrees with a certain co-triple cohomology. So it really is a nice construction of a very standard thing. Okay. Okay, let's go on. Special cases, okay. We've said Baues cohomology can be generalized, but it also generalizes itself many existing things. This is back from Bauer's original paper, the Baues-Wirsching paper. So one thing you can quickly see is that if you look at the factorization category, in the factorization category, you take the domain and the target. Okay, well, the domain of the factorization category, the domain of an arrow is an arrow, and the codomain is another arrow. Okay, and morphisms, well, one was going backwards because factorization category, you have factorization backwards, then up, then along. Okay, so domain and codomain will give you a natural map from the factorization category to C op times C. Okay, so like a bimodule category. Okay, and you can do the projection to one factor. You can do the quotient to get down to the fundamental group of the category or the fundamental groupoid, or you can just take constant coefficients. Okay, so this is a sequence of functors, and this means if I start anywhere, if I have a map from C to abelian groups, or if I have a map from pi1 C to abelian groups, or if I have a map from C op times C to abelian groups, if I can compose it with the appropriate functors, I get a map. I get a natural system. I can pull back. I can pre-compose to get a natural system and get a functor from FC to the category of abelian groups. Okay, so this is how Baues and Wirsching sold their construction, they said, well, there's all the previous cohomology theories that we can find are examples. We can do Hochschild-Mitchell cohomology just by saying, well, if you're given a bimodule structure on C, well, you just precompose with pi and you get a natural system. And the Baues-Wirsching cohomology with this natural system is just the Hochschild-Mitchell. It's the same chain complex. It's the same cochain complex. So Baues-Wirsching cohomology generalizes Hochschild-Mitchell. It generalizes cohomology with categories in a C module. So if you take some F from C, precompose with pi and with P, then you take Baues-Wirsching cohomology, you get back the cohomology with coefficients in the C module. Same thing with local coefficients. If you start with a local system, start with a functor on the fundamental groupoid of C, okay? Or if you take a trivial system with coefficients, just a single abelian group, okay? So you can say the cohomology with coefficients in an abelian group is an example of Baues-Wirsching cohomology with this particular trivial natural system. It's the natural system which just gives the abelian group A on all of the factorization category. So the constant natural system on A. Okay, so Baues-Wirsching cohomology does generalize all of these previous definitions of cohomology from the literature. Okay, now I want to go the other way. Now we're going to go to, well, we're calling it Thomason cohomology. I think the name is probably due to, well, maybe we baptized it ourselves. Maybe it came from Chuck Weibel. Yeah, maybe Weibel called it Thomason systems. We decided to call it Thomason cohomology. So Thomason looks at coefficient systems which start not in the factorization category, but in this common category, this category of elements or category of simplices. Okay, so this category of simplices of a small category or category of elements is, well, delta over C. So just think of it as the category whose objects are all simplices in the category, in the original category. Okay, so all elements of the nerve of your category. Okay, so F is a map from N to C. So F is a string of N composable arrows. So F is an N simplex in C. Okay. And if you want a map from NF to MG, so a map from an N simplex to an M simplex, then you just take a morphism in delta, take an arrow in delta, take a non-decreasing function, which sends the selected element, sends a selected N simplex to the selected M simplex just by precomposition. Okay, so it's just a slight enrichment of delta. Okay. Okay, so you've got the category of elements of C, you've got your simplex category of your category C. Okay, you could also think of it as the Groton deconstruction, or the opposite of Groton deconstruction of the functor from delta up to set given by the nerve. Okay, so yeah, there's some other shorter ways of saying the same thing. Okay, that's going to happen a lot in this talk. I'll go back and say things again in a more concise way. Okay, so a Thomason natural system is just a functor from delta over C to abelian groups. Okay, so you have an abelian group for each element of the nerve, and for each simplicial map in delta, you have I'm calling it theta hash. You have a comparison between the abelian group associated to F and the abelian group associated to G. Okay. Okay. So once we've got these natural systems, we can then use these as coefficients for a nice generalization of Baues-Wirsching cohomology. So this is the next cohomology I want to look at. The Thomason cochain complex is just, well, I'm simplifying the previous definition a lot. I'm going to say, well, let's again take the product over all elements of the nerve. That's what I did before, of these abelian groups. Okay, so I've got all these abelian groups. I take their product over all elements of the nerve, and I take this alternating sum of DIs. Okay, So how do I define this? Okay, so I've got this product over all elements of the nerve of the abelian group TF, and this product of the abelian groups TG. Okay, and I define it as the alternating sum of these DIs. Okay, well, this DI is going to be induced by this coface map here. Okay, so you just say, well, if you've got this cochain, a cochain in here is an element indexed by Fs. Okay, so DI of an element indexed by Fs is the you use the map given by the natural system to the applied to the elements indexed by G, where you take the coface map precomposed with G. Okay, again, I will simplify that even more later, so don't worry about that. It's a bit hard to decipher. But the important thing is that if you want to define a map from the product to the product, okay, you look at the target, okay, you define it on each component of the target by saying what it does on each component of the source, on the corresponding component of the source. Okay. Okay, so that's the cochain complex, and then, not surprisingly, we define the nth Thomason cohomology as the nth cohomology of this cochain complex. Okay, so we've now got another definition of cohomology of categories. Okay, Thomason cohomology of categories. Okay, so here's what I said about simplifying a bit more. You can do what's called co-simplicial replacement. Okay. So you've got this functor T, this Thomason natural system from delta over C to abelian groups. Okay, you can compare this with the I'm citing Baues-Wirsching, but it appears in lots of places. The co-simplicial replacement of this functor is a functor. Well, as we said before, is this functor, this co-simplicial object. Okay. And with these structure maps we already set. Okay, so I'm just saying this is a well-known construction. The structure map from the nth to the mth level of the products is just requiring that the projection on one of these is given by the component given by one of these followed by this induced map. Okay, but leave that there. I just want to say it's also known as the co-simplicial replacement. Okay, so we'll come back to that later. Okay, so the idea is that the Thomason cohomology is a cohomology of a very naturally defined cochain complex. Okay. Okay, why is it generalized Baues-Wirsching? Why do I say that Thomason generalizes Baues-Wirsching? Okay, well, I've already mentioned this long edge map. Remember when I said we had an n simplex, so a sequence of n composable arrows. I can take the longest edge of the simplex, which just corresponds to the longest edge corresponds to the composite of all of these arrows. Okay. Well, in delta over C, the objects are the n simplices. In the factorization category, the objects are the arrows. So this long composition map, compose them all, gives a map on objects, and you can extend this fairly easily to a map on morphisms. Okay. So on objects, we already said what it is. So on an M simplex, we just compose them all. So that's the definition on objects. Okay. On morphisms, well, if we're given a morphism that's the first time I've actually said what the morphisms of this category are as a diagram. Okay. So a morphism in the category of simplices, so this in the simplex category from F to G is just any simplicial map here, which makes this diagram commute. Okay, so F is given by theta followed by G. So F is actually G with some extra simplicial information here. Okay. Okay. Well, the long edge of this, or the long edge of F, is going to be this. It's going to be a map from D, from the abelian group D of theta 0. Okay, because 0 here goes to something here, theta 0, and then G of this. Okay, so C0 is actually D of theta 0. Okay, and Cm, the last object here, goes to theta m here, might not be n. Okay, so D of theta m. Okay, so you've got this lambda f here going from C0 to Cm. but it's also going from theta 0 to theta m. So you can factorize the first few arrows, give you a map from d0 to d theta 0. If theta doesn't send 0 to 0, this map is non-trivial. Okay, then you do lambda f, and then you have the map from theta m to n, which isn't trivial if m is not the endpoint n. Okay, so this gives you a map from the simplicial category, from the simplex category to the factorization category. Okay, and it all depends on whether theta preserves the endpoints or not. If theta preserves the endpoints, then the image of this arrow is an identity arrow. Okay, if theta 0 equals 0 and theta m equals n, this is the identity arrow if theta preserves endpoints. Okay, so this gives you a nice comparison map from delta over C to f of C. And we add this the chain of comparison maps before. So before, we had a comparison map from FC to C op times C, and a comparison map from C op times C to C, and to pi 1 of C, and to the trivial category. Okay, and we just add this to the beginning of the chain. Okay, so in particular, any Baues-Wirsching natural system, any natural system of Baues and Wirsching from the factorization category of abelian groups will give us a Thomason natural system from the simplex category of C to abelian groups, just by composing with this natural comparison map. Okay. Okay, so this means that we can state this theorem and check it's true. It's even true on the complexes themselves. The cochain complexes we've set up are the same cochain complex. If you take a Baues-Wirsching natural system and convert it to a Thomason natural system and take the Thomason chain complex, you get the same cochain complex as you would have done doing the usual Baues-Wirsching cochain complex. So they've got the same cohomology because they were the same cochain complex. So it really is an easy generalization. Okay. Okay, so Baues-Wirsching cohomology is easily generalized to something with slightly more general coefficients. Okay, there's also probably an older definition of cohomology. Well, maybe they didn't mention cohomology, but it's almost there. I mean, in one of the books of Gabriel and Zisman, you can extract a definition of cohomology of simplicial objects. Okay, so given a simplicial set, you can take the category of simplices. The category of simplices of a simplicial set. It's again, you take all the elements of your simplicial set. Okay, take all the elements in every dimension n. Okay, and morphism is just a simplicial map from n to m, which sends the given simplex x to the given simplex y by precomposition with sigma. Okay, so again, you can imagine this triangle. Okay, and then we can invent this name. A Gabriel-Zisman natural system is a functor from the category of simplices of our simplicial set x to abelian groups. Okay, and we can define the Gabriel-Zisman cochain complex, and this probably does come from their paper or from the book. Okay, same as before. We can define the Gabriel-Zisman cochain complex, take the product of all of these abelian groups for every simplex sigma n, okay, and define the alternating sum of these maps whose components are just the obvious things induced by the coface maps. Okay, so given this functor t, you can define a nice cochain complex. We're calling the Gabriel-Zisman cochain complex. Okay, well, I won't read that any slower because again, I will give a slightly more high-level definition in a second. Okay, but suffice it to say, the Gabriel-Zisman cohomology is the cohomology of this cochain complex. Okay, and I want to see that the Thomason cohomology is a special case of the Gabriel-Zisman cohomology because we know a small category is a special case of a simplicial set. Okay, you take the nerve of the category, you get a simplicial set. Okay, and you can think of this as an embedding of the category of small categories into the category of simplicial sets. Okay, so our simplex category delta over C is the same thing as the simplex category delta over the nerve of C. Okay, In particular, our Thomason natural systems on C are the same as our Gálvez-Wirsching natural coefficients on the nerve of C. So it's the same. The source is the same category. Okay, or isomorphic categories. So if you take any small category, take any Thomason natural system, okay, then the Thomason cochain complex of C with coefficients in T coincides with the Gálvez-Wirsching cochain complex of the nerve of C with coefficients in the associated natural system. It's the same functor T really. There's just an isomorphism between these categories. You just identify them. Okay. So Gálvez-Wirsching cohomology and Thomason cohomology are the same thing. Okay. You just extended from categories to all simplicial sets. Okay. The things you can do with categories which you can't do with simplicial sets, but anything you can do for simplicial sets you can do for categories. So Thomason is the restriction of a simplicial definition just for nerves of categories. Okay. Okay, so we have Gálvez-Wirsching has a special case Thomason. Thomason has a special case Baues-Wirsching. Baues-Wirsching has a special case Hochschild-Mitchell, etc., etc., etc. Okay, so we're building up these towers of theories. Okay, let me go the other way. Let me go to two categories. Okay, so this isn't too difficult. First of all, we need to set up what is our indexing category. We can define the category of simplices of a two category. So now I'm talking about a strict two category. There's no lax morphisms. Composition is associative on the nose, etc. Okay, but we could also have lateral lax functors here. Okay, the functors don't have to be strict. So we can define the category of simplices delta over D. Okay, look at all lax functors M to D, and whenever you want to have a comparison between this functor A and this functor B by some functor theta, okay, because the category of categories is a two category. Okay. Sorry, because D is a two category. We can look at the category of factorizations as well. Two different definitions here. Sorry, I should have done this in two separate slides. Okay, that's just one slide. Okay, so first we'll define the category of simplices, then we define the category of factorizations. Okay, category of factorizations is, well, you look at the objects of D. Sorry, the objects of the category of factorizations are the arrows in D, just as before, and the morphisms are, well, they are factorizations, okay, but now we have a two morphism. Okay. Okay. So I'm feeling there's a mistake in this diagram here. There should be a two cell between these. Okay. Okay, because D is a two category. So we're not using the two category structure here. Okay, I will try and update this slide before it's made even more public. Okay, so here's the slightly unexpected result. If you look at the simplex category of a two category and look at the factorizations of a two category, okay, there is again this natural transformation. Okay, so what we have to do is say, well, if we're given the long edge of B and the long edge of A, we have to somehow construct some, well, we know what to do, take all the maps between 0 and theta 0, and all the maps between theta n and n, okay, and then somehow build a two morphism from the data we're given. Okay. This two morphism built from the data we're given is, well, it's the fact that we have our A and B are lax functors. So A and B have some extra given data. They are lax functors. Okay. Okay, so there is a way of doing this. We have it typed up in a preprint, but it's not. I mean, it's not suitable for putting on a slide. Okay, just believe me, there is a definition. Okay. The important thing is, again, if it preserves endpoints, then we've got the identity errors here. Okay. And we can say explicitly what happens for the outer co-space map. So if we have the forget the first object or forget the last object, okay, that's the thing to worry about. If we don't have theta 0 equals 0, it might be we forget the first object. If we don't have theta m equals n, we forget the last object. In these two cases, we can see exactly what's happening, okay? We have a comparison between the long edge of A and the long edge of B using the lac structure on B, the lac structure 0, 1k here, okay? Or the lac structure 0, kk minus 1 here, okay? So we can see this one corresponds to a pre-composition, and this one corresponds to a post-composition, okay? So it's fairly easy to write down the special cases. So we do have a comparison. Okay. Now, we can then define a Thomason natural system on a 2 category as a functor from this new category of simplices of a 2 category. Okay. We can define its co-simplicial replacement as this co-simplicial abelian group, just as before. And let me just give you the highbrow definition now. We can define this immediately by saying, well, you have a functor on this category to abelian groups. You have a functor on the same category to delta. Okay, just take the right Kahn extension. Okay, take the right Kahn extension of T along this projection, and that gives you this co-simplicial replacement. So what I said before about co-simplicial replacement is just condensed into saying it's the right Kahn extension. Okay, so we have a Thomason natural system given on the category of simplices. We have a co-simplicial replacement of this functor, giving co-simplicial abelian group. And you can define the Thomason cohomology of your 2 category with coefficients in the functor T as the cohomology of the cochain complex given by the co-simplicial replacement of this functor T. Okay, so that's the sort of one sentence definition of Thomason cohomology, in this case for 2 categories. Okay, it's the cohomology of the co-simplicial replacement of the functor. Okay, don't need to be explicit about anything here. It's all hidden in this right Kahn extension definition. Okay, we can do the same for Baues-Wirsching cohomology. Okay, we've got this factorization category on a 2 category. Okay, and a Baues-Wirsching natural system, we know there's a comparison map. So Baues-Wirsching natural system induces a Thomason natural system. So we can be lazy and we can use this. We can use this to define Baues-Wirsching cohomology. We can define the Baues-Wirsching cohomology as a special case of Thomason cohomology. Okay, so we define the Baues-Wirsching cochain complex dk of a 2 category D with coefficients k from the factorization category to abelian groups as the Thomason cochain complex we just gave above as the co-simplicial replacement of lambda star k. Okay, so think of k as okay, so as I was saying, the Baues-Wirsching cohomology is just the Thomason cohomology of the precomposition of the coefficient system with this with the very nice comparison between the simplex category of the 2 category and the factorization category of the 2 category. Okay. Okay, so this works for 2 categories. Let's see how much further we can push it. Track categories. Okay, this was good because this was a bit of a motivation. We saw that David Blank and Simon and Paoli had given a definition of cohomology of track categories. So track categories are just 2 categories with invertible 2 cells. Okay, so 2 categories where the 2 categorical structure is invertible. Okay, and if you like cross modules, they're a special case which also have invertible 1 cells. Okay, so given a track category, David Blank and Simone Paoli defined in 2011 a cohomology. And we can see, just by direct comparison, that our Baues-Wirsching cohomology of D, our coefficients and our cohomology coincide with theirs. Okay, so we can recover the Blank-Paoli cohomology of track categories, just as a special case of the Baues-Wirsching cohomology of two categories. Okay, so again, it fits in nicely with things that were just appearing in the literature. Okay, decomposition spaces. Let's get on to something very new. I'm almost on my last slide. So I suppose I'm open for questions. I have to let myself open for questions. Decomposition spaces. Let me just give you a 2-minute spiel about how decomposition spaces arose. Also called two-sequel spaces. So here I'll just say that decomposition spaces that we call them decomposition spaces because we saw them as ways to model co-associativity. So breaking things into pieces is slightly easier than putting them back together. So decomposition spaces are like categories, but you don't insist that associativity holds, but co-associativity should. Okay. So what I'm saying is that there is this two-sequel condition for decomposition spaces, which is slightly weaker than the one-sequel property. The one-sequel property is for ordinary categories. If you know the sequel condition for categories, we can just by a shift in dimension, you get the two-sequel property for decomposition spaces. And two-sequel spaces is the Dikov-Kapranov term for these objects, and decomposition spaces is the Gálvez-Tonks, Gálvez-Tonks definition of nomenclature. Okay, same definition really, but it's quite well disguised. Okay, so one of these 5 author papers, Julie Bergner, Osorno, Vavreli, Claudia Schaumbauer, showed a simplicial set has the two-sequel property, so it's the decomposition space, if and only if this edgewise subdivision we've mentioned is actually a category, or the nerve of a category. Okay, so you can classify simplicial sets which arise as nerves of categories by the one-sequel condition. Okay, and if the edgewise subdivision of X has the one-sequel condition, so it's a category, then X is a decomposition space. Okay. Okay, so in the one-sequel context, yeah, edgewise subdivision, we've seen edgewise subdivision is the simplicial counterpart of the factorization category. So we can just move from the factorization category for Baues-Wirsching cohomology to the subdivision of a simplicial space or of a decomposition space. Okay, if X is a decomposition space, okay, then sub X is a category, okay, by this Bergner et al. Paper. Okay, sub X is a category, so we can define coefficient systems D on this category. Okay, so our coefficient systems will be on the category given by the edgewise subdivision of a decomposition space. Okay, if X is a decomposition space, the edgewise subdivision is guaranteed to be a category. We can use it as the indexing diagram of our coefficient systems. Okay, if we didn't have an indexing diagram here, if we didn't have a category, we couldn't do this. Okay, so we can define Baues-Wirsching cohomology for decomposition spaces. Okay, we could also easily, much more easily, define Thomason cohomology for decomposition spaces, because Thomason cohomology, well, we just take our coefficient systems using the simplex category. So it's just like saying, well, if X is a decomposition space, well, it is a simplicial set in particular. If it is a simplicial set, then, well, we can use Gabriel-Zisman cohomology and call it Thomason cohomology. Okay, so we can define Thomason or Gabriel-Zisman cohomology with these coefficients. We can define Baues-Wirsching cohomology with these coefficients using the result that the subdivision category is a category. Okay, so it's the counterpart of the factorization category as we know. Okay, and once again we have this natural transformation from the category of simplices to the subdivision category. Okay, so it's not just it is a category, there is a natural transformation here. Again, that's not so easy to write down. Okay, this is a category and this is a functor. This is a natural transformation. Okay, so we can define cohomology decomposition spaces. Okay, And that's about all I have really available to say in public. My next slide is a list of things that, yeah, probably we would like to do, and we would like any contributions, anybody who has any brilliant ideas. Okay, so one obvious thing we can do, this is really a bit obvious, we could take simplicity enriched categories. A simplicity enriched category has well, you know from Lurie, it has a homotopic coherent nerve, so you could then use the Gálvez-Wirsching cohomology of this. Okay, you could, if you started with a 2 category, take the nerve in one direction, you get a simplicity enriched category, and the homotopic coherent nerve will agree with what we already defined. So in this case, we don't get anything new. Okay, so this is a test case, we don't get anything new for 2 categories. We could do bi-categories instead of strict 2 categories using, I think some people call it the Duskin nerve, some people call it the geometric nerve, maybe there's a street nerve around here somewhere. So once again, you could, for bi-categories, you could take the appropriate nerve to get to simplicial sets, use the Gálvez-Wirsching cohomology there, and you could define Thomason cohomology of a bi-category there. Don't know what properties it would have. Okay. What we can't seem to do is define Baues-Wirsching cohomology. Okay, for Baues-Wirsching cohomology, we need some idea of a factorization category. And we don't have a strict definition of a factorization category of a bi-category. Okay, so the lack of associativity on the nose means we don't have a factorization category, not a 1 category anyway. Okay, so we can't define Baues-Wirsching cohomology of bi-categories. Okay, what else can we do? Well, naively, given a quasi-category model of an infinity category, so given an inner Kahn simplicial set, we can take the Gálvez-Wirsching cohomology. So we do have a naive Thomason cohomology of infinity categories. Okay. And finally, I want to say something which is not okay. The reason it looks a bit ill-defined is I'm not quite sure yet what I mean by it. There seems to be some relation to K-theory in the sense that the edgewise subdivision is in some sense a one-sided inverse to Waldhausen's S dot construction. So the S dot construction was used to construct K-theory. If you do the edgewise subdivision of the Waldhausen's S dot construction, okay, you get something pretty big, but it turns out this data is, well, can be recovered from the category of spans or the category of correspondences or its nerve in your original category. Okay, so you almost get back the original category by doing the edgewise subdivision of this K-theory construction. Okay, so I'd like there to be some, I'm very vague here, I'd like there to be some relation to K-theory and these strange Thomason cohomologies generalizing Baues-Wirsching cohomology. Okay, and I will stop here a bit early. Okay, thank you for listening.